welcome to students. In this lecture we are going to look into strongly transitive systems. We are going to continue with what was done in the previous lecture and we recall here. So, the rest of the things like X is a perfect space, compact space, right, and our system, right, that remains the same. We simply recall the definition of the backward orbit that we had taken up. So, the backward orbit is basically the union of f minus nx, right, for n going from 1 to infinity. Now, we may not be interested in the backward orbits, right, the full backward orbit. So, we would like to see that we want to look into a backward orbit up to certain level n. So, for that, for n in n, we define this backward orbit of x for the level n. We define this factor to be the union of f inverse of x or f minus n of x, right, when I am looking into my n going from 1 to capital N. So, basically we are just interested in a or one can say that one is interested in a finite backward orbit. So, you are looking into a backward orbit up to a certain level n, you are not looking into the complete backward orbit. So, we define this factor and again I would like to recall the hitting time sets. Now, we know that we have seen this hitting time sets nxv, right, which is basically the set of all n in n such that f n x belongs to v. We had looked into this hitting time set when we were discussing recurrence, and then we have this hitting time sets n u v to be the set of all n in n such that f n of u intersection v is non-empty. And now, we define another kind of hitting set which we write it as n u x, which is basically the set of all n in n such that x belongs to f n of u. So, we can think of this new kind of hitting set that we have defined here. So, I am looking into this part, this is something new that we are considering here. So, we are looking into all those images of u, right, all those images of u under n, so f n u for which contain the point x. Now, we will look into a theorem and we have discussed some properties of that, but we will now push that up in terms of a theorem. So, we have a theorem here that for the system x f, the following are equivalent. So, the first thing that we want here is that x f is strongly transitive. The second is we want that for every x in x and non-empty open u contained in x. We want this new kind of hitting set that we have defined n u x to be non-empty. So, for every x in x and you can take any non-empty open u in x, then we find that this hitting set is non-empty. In fact, the compactness of x will basically say that this hitting set will be infinite. Then we have for every x in x, the backward orbit of x is dense in x. We have already seen that these two properties are equivalent. This is just a demonstration that yes, your x can be written as union of f n u, right, and so definitely your n u x will be non-empty, and from compactness we can say that it will be infinite actually. Then this is also the same thing which we have already seen that in the previous lecture that if xf is strongly transitive implies that for every x in x the backward orbit is dense. And the fourth property which I want to write here, which is something new, is that for every x in x and epsilon positive, there exists an n, some integer, such that if I am looking into my backward orbit of x of level n, then this is epsilon dense in x. Now, just want to recall that what do we mean by epsilon dense, right? We say that something is epsilon dense if basically it forms a net, right. So, it is an epsilon net basically in x. So, that means you take an epsilon ball centered at each point here, right, that covers the whole of x. Fine. So, this is what we want to say is that for every x in x, you take any x here, you take a positive epsilon, depending on that x and that epsilon you get an n such that this finitely many points here that you get here, right, this will be epsilon dense in x. And that is very simple to see that because you know that your orbit is dense in x. So, you are trying to take, so you start with say you start with the inverse image of x, right, take epsilon neighborhoods there, right. In fact, you take epsilon neighborhood for every point in the backward orbit, and then since x is compact, right, by compactness you will get something like a finite subcover, right. So, what you get is something finite, right. So, this finitely many epsilon balls will be covering x, and so you get that the backward orbit of level n happens to be dense. Now, before we go to something else, I would like to recall a definition. We have n to be a set of natural numbers. So, we call A subset of n to be synthetic if the elements of A elements in A occur with bounded gaps. So, what does that mean? It means to say that there exists some m in n such that A meets every interval of length m in n. So, such a set is called synthetic, where the elements they appear with bounded gaps. And now, we have this result, again I am putting that in terms of a theorem here. So, we have this theorem here. So, for the system xf, the following are equivalent, and the first condition is that xf is very strongly transitive. And the second condition is that for all epsilon there exists an n in n such that the backward orbit of x of level n is epsilon dense in x, it is epsilon dense in x for every x in x, right, for every x in x. So, here our n does not depend on x, basically depends on epsilon, and the same n works for all x. And the third thing which we have here is that if for every x in x and every non-empty open u contained in x, this hitting time set NUX is a syntactic set. We have these conditions for strongly transitive, and I am not exactly going to prove this part, but one can think of this factor that when you are looking into a strongly transitive system, what happens here is that finitely many images of u, right, covers the whole of x. So, what happens here is you have just finitely many of this n's, right, which happen to be, just take epsilon neighborhood there, let your u be an epsilon neighborhood of x, right, then the finitely many images will cover the whole of x, and so what you will get is that the backward image, right, finitely many will be epsilon dense in x. And similarly you can think of this factor that you look into n u x, right. Now what happens is, since my x can be covered by finitely many images of u, right, so I could take up any epsilon neighborhood. So think of any epsilon ball, just take any epsilon u to be any epsilon ball, right, then for that epsilon ball that u is open. So finitely many images of that would be covering the whole of x, and hence you take any x, right, irrespective of what x you take up, you take any x, right, it will lie somewhere over here. In fact, the entire orbit will be lying somewhere over here, and so what you find is that this particular set happens to be a syntactic set. So x belongs to FNU happens to be a syntactic set, because then your orbit of x is just moving around the finitely many aspect, right, just is moving in the finitely many balls, right. So you find that x lies somewhere or the other, right, because these are finitely many balls which cover the whole of x, right. So you find this to be a syntactic set. In fact, one can see it in a more better way. Supposing now I have x to be written as union of FNU, say n going from 1 to n. Now what can you say about your fx? I can apply f on both the sides. So this happens to be, again I can say that this is union of n going from 1 to n, f of n plus 1 u. Let me take fkx, right, this is also going to be union n going from 1 to n, f of n plus ku. So what can you say about your, now we know that all of this is going to be x, right, this is also equal to x, my system is surjective. So this is also x, this is also x. So what happens here is that if I look into for every x in x, take any x here, right, what happens is, what is NUX, right, NUX is going to be like maybe some n from here, right, but then it has to be something from here, it has to be something from here, right. Then where does it meet? Then there is some kind of a bound here, such that when you consider NUX, right, what are all the elements of n which come here? Then they come with bounded gaps, because ultimately you just have something common here, right. So every interval in that case, supposing this is n, I can say that in a gap of length n, right, I am looking into a gap of length n, right. So all the elements in NUX, they will occur in the gap of length n. So this set happens to be syntactic. So all I can say is that NUX, right, meets every interval of length n in n. So this happens to be a syntactic set, and from this I can say something more, that x is very strongly transitive, that gives me that this is a syntactic set, right. So if I have any pair of open sets, so for every pair UV of non-empty open sets what happens to NUV? Supposing my X was in V, right, then this would have been contained in NUV. So, what can we say about NUV, right? NUV is also a synthetic set, right. So, NUV is a synthetic set. This observation that this is a synthetic set, right, and this happens for a very strongly transitive system, this observation is important. So, I am defining something else which we have not defined that earlier, right. So, we defined that for a system XF, a point x in X is called, I want to specify this point, we have not taken up this definition earlier, is called an almost periodic point if, now there are various ways of defining this. We define this in a more geometric manner. If for every epsilon greater than 0, there exists a k in n such that if I look into my orbit of X, this orbit will be contained in, right, the intersection over all n in n. What intersection I am taking? I am taking a ball of radius epsilon centered at Fnx, right, union a ball of radius epsilon centered at f plus 1 x, union a ball of radius epsilon centered at Fn plus kx, right. This is the same k that we have taken up here. So, if I take this ball, right, at these points in the orbit, right, k consecutive points in the orbit, any k consecutive points in the orbit, if we take an epsilon ball around them, we would find that the orbit of X is completely contained inside that set, and this is also sometimes called as uniform recurrence. So, say I am looking into some point X, right, then I know that if I have X, right, I am taking an epsilon ball around X. So, you have this point X and you are taking an epsilon ball around X, it is taking some kind of epsilon ball around X, then you know that you are looking into X, then you are looking in an epsilon ball around Fx, right, and so on Fk plus x, and then again what you find here is that some iterate of f, right, it will lie Fx, Fkx, right, where is Fk plus 1x, right. So, what you will find is that somehow it will Fk plus 1x, Fk plus 2x, one of them will definitely come inside here, right. So, what you find here is that there is, since there are finitely many balls, right, and we are dividing all these orbits completely over here, then you will find that the set of all iterates of x, right, which basically not just that x is a recurrent point, what we find is that the iterates of f which converges to x, right, they also come up with some kind of a bounded gap. So, what happens here is my x is not a periodic point, maybe it can be a periodic point, all periodic points are almost periodic, right, but x need not be a periodic point necessarily, but even if x is not a periodic point, but then there is a bound m such that if I start with x, then there is one orbit between x, say I start with x, fx and so on up to fmx, right, one of the points would have definitely come inside this point. Then again we start the same cycle again, one of them would definitely come up over here. So, now if I am looking into, supposing I say that since this is a recurrent point, because something will definitely come here, for every epsilon something is coming here. So, this happens to be a recurrent point. So, this is a recurrent point, but not only recurrent point, this is a uniformly recurrent point, because whatever comes, the sequence that converges, right, the sequence of iterates of x that converges to x, right, this is occurring uniformly. So, there is some kind of bounded gap which is coming up there. So, you find that this is a uniform recurrence. So, this kind of recurrence is a uniform recurrence. and that is what is meant by almost periodic point. So, this is not a periodic point, but with bounded gaps, right, the heat rate, right, or I should say bounded heat rates of F will definitely lie close to x. So, x is not a periodic point, but it is an almost periodic point, right, although all periodic points are almost periodic points, but we do have almost periodic points without the point being periodic. Now, very interesting to observe that supposing this particular, I have a point x such that this x is an almost periodic point, then what can we say about the orbit closure of x? So, what can we say about this particular system? X is an almost periodic point, right, and for an almost periodic point, if I am looking into its orbit closure, because its orbit is anyway lying over here, right, supposing I am looking into its orbit closure, I am not going elsewhere, right. What happens to this set? So, it is a little bit, it is, you will need to think a little bit, but you can see that this is a minimal system. And why this is a minimal system? You take any closed subset of orbit of x, right, you will not find it to be invariant. Take any closed subset of orbit closure, it is not going to be invariant, right. So, this system happens to be minimal with respect to this property of being closed and invariant, and hence this will be a minimal system. Conversely, you can say that every point in a minimal system happens to be an almost periodic point, right. So, every point in a minimal system is an almost periodic point. Now, this is one of the properties of minimal system, that each and every point is almost periodic, that means each and every point is recurrent, not just recurrent, it is basically uniformly recurrent. This concept is there only true for the minimal system, that every point happens to be uniformly recurrent. And now, if we try to see what happens for a uniformly recurrent system, so our system is uniformly recurrent. Now, what happens in that case is that for a minimal system, right. So, for minimal system, now minimal system every point is uniformly recurrent, or every point is almost periodic. So, you can think of this scenario here for a minimal system, and what does that give you? That gives you that for a minimal system, this hitting time set NUV is a syndetic set. So, this set is a syndetic set, and this set is a syndetic set is one of the properties of minimality. What we find here is that this is basically a property of minimality, but for our very strongly transitive system also, right, we have the same property holding true. Although we know that there can be very strongly transitive systems which are not minimal, right, but still we find that this property is basically holding for very strongly transitive system. So, this is basically a property of minimality. So, is there really any kind of relation between minimality and very strongly transitive? So, we try to see that in the next theorem. So, let me write the next theorem here. For the system XF, where F is a homeomorphism, the following are equivalent. The first condition that we want is XF is minimal. The second condition that we want here is XF is very strongly transitive. And the third system, the third condition here is XF is strongly transitive. What we want to say here is that if we have a homeomorphic, basically if a system, our map is a homeomorphism, so in an invertible system we have these three conditions to be equivalent. And the proof is again not very difficult here. So, if we try to see this proof, right, we have seen that one implies 2, right, implies 3, we know that part. So, conversely, let us assume that 3 holds. And what is the meaning of 3 holding is that for non-empty, any non-empty open U subset of X, right, we can write X to be the union of F and U, n going from 1 to infinity, but F is a homeomorphism, right. So, each of this F and U is open. So, what I get here is the F and U's, they give me an open cover of X, and by compactness of X this should have a finite subcover. So, there exists an n, some integer n, right, such that X is written as 1 to n F and U, and well, so basically I have my 3 implies 2, and again if I assume that X is from 1 to n F and U, I again know that F is a homeomorphism here. So, I can continuously apply F inverse again and again, right, applying F inverse again and again, I can say that X is same as union n to n is from 1 to n of F minus n U, and that again I can think of saying that this is same as n going from 1 to infinity F minus n U. That gives me that the orbit of X will be dense, right, because I know that X can be written over here. So, I take any point X, right, then there will be a U such that Fn of X will belong to U, and this is, since this is true for any non-empty open U, for any non-empty open U, my X can be written in this form. So, if for every X in X, right, for every X in X and every open set U, right, there will exist an n such that F and X belongs to U, right. So, this gives me that the orbit of X is dense in X for every X in X, and so my 2 implies 1. So, when we have a homeomorphism, these 3 concepts are coinciding, they are the same, but we know that in general these concepts are not the same. We have seen an example of a minimal system which is not very strongly transitive. What about very strongly transitive and strongly transitive? Are they the same concepts? We know that one implies the other, that is very well clear from the definition, but are they the same thing? Do we have something to differentiate them? So, let us try to see an example here. Now, we are not getting into further example, we are just looking in our sigma to be a set of infinite sequences of zeros and ones, and we consider the system same example that we have been working out. But now there is something that I would like to see inside this particular system. So, let me take the sequences. I am looking into the set of all sequences of the form 0 to the power k, then I have 1 to the power t1, then we have 0 to the power 3 raised to n1, then we have 1 to the power t2, then 0 to the power 3 to the power n2, 1 to the power t3, 0 to the power 3 to the power n3, right, and so on. I am looking into set of all such sequences where my k is 0, k can be 0 also, that means I have nothing over here, right, k equal to 0 means it is not 0 to the power 0, so basically means that I have nothing over here, this is the empty word here, and k is any number, any finitely, so I can have any finite string of zeros basically, followed by, this is a nice pattern, I have something like 1 to the power t1, 0 to the power 3 raised to the power n1, so that means the zeros that occur between two ones, right, they occur in powers of 3. So, the number of zeros between any two ones occurs in powers of 3. I have this system and my Ti and Ni, they can be any element in N. Now, I am looking into this particular set of all sequences. I want to look into the closure of all the sequences, that means I am not only looking into these sequences, I am collecting their limit points also. So, we will look into the closure of these points and we call such a set to be X, where I am looking into this closure in sigma. So, look into the closure of this set in sigma and we take X to be this closure in sigma. Now, observe one thing, what can you say about sigma X? If any point is a limit point also, right, the initial part will have to be something of this form. So, any sigma X will be basically a subset of X, so that means X is invariant under sigma, right, and so I can think of my X along with sigma, right, is a dynamical system. Now, we are interested in looking into what kind of dynamical system have we obtained here. So, we take any x in X, or it will be more easy to say that we take any cylinder set here, right, any basic open set here. So, any basic open set here would be of the form, say I am looking into some sequences, right, it should coincide with those sequences. Now, whenever I look into any sequences, that sequence will be of this particular form only, any sequence will be of this particular form only. So, we take, say, let W1, W2, Wk be any finite sequence in, say, some x. I want this finite sequence to occur in some x in X, right. So, I am looking into the finite sequence of this kind only. Then this is a cylinder set. Or I can say a basic open set. This is a basic open set in X, and I am taking that I start with this factor and I am trying to look into all unions. So, basically I am looking into all the images of all such points which started with W1, W2, Wk, I am looking into the images of all such points, right. So, we find that the union of sigma n of this particular set, when I am taking my n going from 1 to infinity. Now, think of that, what are all the points which are coming up, right. Definitely all points of this form will come up, Now think of this, here I am considering T1, T1 could be anything, right, N1 could be anything. So, I am considering all these possibilities of N1 and T1, right. So, all can come up over here, I need infinite there. Then I am looking into the limit points. Now, when I say that something is a limit point, right, it is a limit point of these kind of sequences, then these point of sequences there will be, say supposing say my y happens to be a limit point of such sequences, then what you have is you have a sequence of some elements of this form which are converging to y. So, what can you say about y, right? The initial segment of y, right, would be something of this kind. So, that means when I am looking into this part, right, I am including all the limit points of such sequences, and we find that our x can be written as the union of all such things for every open. Now, I am looking into this to be some basic open set, right. I can say that for every basic open set I can find that x is written as, x can be written as union of n going from 1 to infinity sigma n of this particular truth, right, and this is true for every basic open set. Now, this is interesting, since this is true for every basic open set in X, I can write my X to be the union of all such images of open sets, right. What we can conclude here is that this particular system will be strongly transitive. So, X sigma Now, my query goes something else. Can I say that I can think of this to a finite level and say that all elements of X are contained here? Supposing I start with any word, right. Now, this word will have finite length, fine. So, if I take a finite image here, right, since my T I N I can be anything, right, this is a gap of 3. In a finite way, right, a finite union, right, may not be equal to X, right. There will be some points which will be there will be some points which would be getting excluded over here, right. So, if I look into this particular system, right, this particular system will not be very strongly transitive, because we cannot stop it after some time. We need that infinite iterations, we cannot stop them at particularly finite. So, we can observe that very strongly transitive. So, we have an example of a strongly transitive system which is not very strongly transitive, and we would be interested in looking into what can we say about this relation with other stronger forms of transitivity that we have seen. So, let us look into this example once again. So, our example is the closure of these systems. Now, think of this example. What we want is that given any open set U and V, right, there should be finitely many. So, you can plug in finitely many say finite sequence of zeros and ones in between, and you can take from an open set U, you can go to an open set V. What we find here is that this particular system is mixing. The reason is that supposing from U to V I could go in one step, right, then I could immediately take another set also, another point also, right, some iterate also, some another point also, such that I can go from U to V, increase a 1 there, right, increase either 1, 2 ones there, or increase 1 more, 3 more zeros there, right. So, we could increase this particular form there, right. So, what we observe is that this particular system is weakly, let us think of weakly mixing here. this particular system is weakly mixing, maybe that is enough for us here. So, this particular system is weakly mixing. So, what do we have? We now have a example of a weakly mixing system which is not very strongly transitive. So, in general we can say that weakly mixing does not imply very strongly transitive. And if we look into the irrational rotation, so the irrational rotation is strongly transitive. But it is not weakly mixing. So, what do we have here is that strongly transitive does not imply weakly mixing. What about the converse part? Does weakly mixing imply strongly transitive? What can we say about the converse part here? Think of that. I know that if my system is a homomorphism, right, if f is a homomorphism here, system is invertible, then my strongly transitive is equivalent to minimality. So, supposing instead of taking a one sided shift, right, if I take the two sided shift, we have already seen that the two sided shift is weakly mixing, right, the two sided shift is weakly mixing, but it is a homomorphism, right. So, it can be strongly transitive if and only if it is minimal, but the two sided shift is not minimal, right. So, in general your weakly mixing also is not strongly transitive. So, these concepts are again very distinct kind of concepts. So, strongly transitive does not imply weakly mixing. So, all you have is your mixing, your weakly mixing, your locally eventually onto, right. All these concepts are interrelated, where some kind of relations holds and some kind of implications hold and some kind of implications do not hold, right. So, in general this is sort of a very mixed up concept here. There are other properties also of this stronger version of transitivity, and since this is a very relatively new concept, there is only something being studied. There is still a lot of chaotic properties that needs to be studied here. Since I do not want to waste much time or get into more details into this one, we are more interested in looking into some more stronger forms or some more chaotic properties of system. So, all I would like to end up here saying that since this is a relatively new concept, many of the chaotic properties still needs to be investigated. So, one can simply say that yes, this particular line of thought is still open, right, and one can work on this further, or I am not sure how and when something more will be done on these properties. There are still other properties also which are studied up, but I have not collected everything in this particular lecture. There is another thing which I noted was that we have studied we have taken up lot of examples, and most of these examples that we are taking up is in the set of sequences. So, we would like to give a little bit more thought to the set of sequences and try to look into the properties of the set of sequences, right, and maybe that will be the topic for our next few lectures. So, let us try to look into, because almost all counter examples we are generating from that aspect. So, we will try to look into that in the next class, but for this class we stop here.